Welcome everyone to the case study Q&A. So again, I'm Thomas. Maybe you heard me last week on the fixed wing just general lecture. Hopefully you've watched the 3 different case studies. So the really nice case studies from David, Mike, and Sebastian. So they're all here. You can see them to answer your questions. So basically we'll just do Q&A. So we could do it 2 different ways. In the fixed wing live lecture, I just kind of had people post questions into the chat, and then I tried to get through them as fast as I could. Since we have 3 different presenters here from 3 different case studies, the other way we could maybe do this is if there's like a raised hand system, and then you could just speak. So maybe, okay, what emojis do we actually have here to use? So there's thumbs up. So maybe let's take a vote. So I'm just going to look at all the chat heads I see here, and if you think that so out of the 2 approaches, so one approach, post whatever you want in the chat, and then the 3 presenters will try and go through each one of the questions. Second option is you raise a hand and they call on your name, and then you can talk to each other for real. So first option, can you give a thumbs up emoji if you think that's the best one? Okay, only 2 for the chat. Okay, and then let's just make sure here for second option, so where you actually get to speak, thumbs up for speaking with raised hands. Also only 2. And no one else has an opinion about this. Okay.
I guess we can
maybe
start in chat and then see how well and how long the questions get.
Okay, sure. Let's do that then. So I guess then, as Mike said, if you have questions about any of the 3 case studies, I guess just post them into the chat, and then the respective case study presenter will try and get back to you.
Hey guys, I quickly need to reconnect, like audio's pretty low and this typically solved it. See you in a second.
So for the exercise, so from Jin Cheng, no, there's no introduction video about the exercise. I did, however, post the so the PDF of the I guess the instructions for the exercise today on the Piazza. So if you want to quickly review that or even start on that, so the files are all there too, the MATLAB files, Simulink files, before tomorrow, then it's probably a nice idea. But there's not too much extra theory to know. It's really just kind of following through the instructions in the exercise, and it kind of tells you exactly what to do. So there's, it's not like a quiz or something.
Good question about the controller at Wingtra. So what we did is basically we had a controller that did know also the inflow of the airspeed, and basically based on that would still scale down the flap deflections. So there's just one controller that could handle it in all conditions. So instead of having 2 differently decided ones, we just had one that was accounting also for the airspeed, for the incoming airspeed, to downscale the flap deflections and also change the influence of the differential thrust that the propellers have. I hope that answered the question.
Yeah, maybe to add on this, I think this is generally something you definitely need to do for hybrid platforms, that you really have a model which captures kind of everything. There are solutions where you try to treat it separately like a multi-copter in hover and just a fixed wing in cruise, and then kind of hope for the best in between, just switching quickly. But like on fixed wing side, we also have like typically airspeed feedback, so that we know that if we go in faster, we have to deflect the control surfaces less to get the same reaction kind of.
Maybe to add on that question, like in the Wingtra case, there were no exact measurements of like the airspeed, no? So you had to guess kind of from the pitching angle deviation what the airspeed effectively is. Did I understand that correctly?
So we do have an airspeed sensor that is attached at the front of the wing. So we do get a measurement from it, but during transitions, it's often not the best measurement, because usually like the way we measure this with a pitot tube, and this pitot tube typically have some angle at which you have a good measurement. So it's kind of a bit a combination that we can then do in the estimator, that we have on one hand the airspeed measurement from the pitot tube, which for most of the cases is good enough. And in the cases where we don't have a valid measurement yet, we can know it based on other things like, though I think for us, it's right now good enough to just use the airspeed sensor, but what you could also do in case it wouldn't be good enough yet is to have some estimate of the power you're currently using and the ground speed that you have, assuming that having a constant airspeed also is equivalent to, or if you have a constant ground speed and constant power that you are using, you can also assume or do calculations how you could get the airspeed. But for us, it was good enough to just use the measurements from the airspeed sensor, actually. So we do have that sensor in case it wasn't clear.
Okay, then the next question concerns the equation presented by Mike. They seem to be complicated, or at least in detail. So for the exam and how much you understand them, I think it's enough to have a high-level understanding here, just to see the different platforms, kind of how we approach the problems of controlling them and modeling them. But we won't question you in detail on these equations. So.
Yeah, I mean, maybe to add on that, I mean, it's always based on the Euler equations. And then the question is, how do you compute the individual force contributions? And this is, in general, like more or less common for the, I guess, for lift and drag. These are more or less common equations. But then, of course, if you want to apply it, you have to do it specifically for your platform. So as David said, I think if you know, or maybe teacher, you can also a bit elaborate on this. But I guess if you know in general how to construct lift and drag equations, this should be fine.
Yeah, so that's true. Basically, the case studies are really more informative, just like extensions of what you learned in the primary fixed wing lecture, how you can apply these things to more complicated problems. So all of these convertible platforms are a bit more complicated, obviously, than just a standard fixed wing and cruise. But for the exam, we'll really only test over the stuff you saw in the first lecture for fixed wing. So maybe there might be a multiple choice on, like David said, a very high level kind of understanding of a difference between the two. But it's not going to be detailed equations or derivations or something like this. Lift and drag, like Mike said, is very important. I think I also mentioned this last week. So definitely know how to formulate lift and drag, where they come from. But otherwise, yeah, the case studies are really more high level.
Okay, then the next question is also quite interesting. So like difference between tilt rotors and tilt wings, and generally which one has like more potential? I think this is very kind of hard to answer question. We can actually make a debate here. What's better, tilt wing, tilt tail setter, or tilt rotor? So I think that's kind of easy out answer. It depends very much on the application, I think, that you really want to target. And between tilt rotor and tilt wing, there are different things. It also depends a bit on like the actual design of a tilt rotor, for example. So if you take big tilt rotors like man ones, like the V22 Osprey, one of the disadvantages of these kind of platforms is that, for example, you have the wing obstructing parts of the airflow from the props, but this is kind of something that you can design away by mounting the props at a different location and still tilt them. So it's kind of depending on the tilt rotor design. For big platforms where you might run into structural issues, which is typically not really the case for smaller platforms because materials scale differently. But for big platforms, having like the rotors, the tilting rotors out on the wingtip might be a structural issue, because then the entire lift in hover is just basically generated at the very outer end of the wing, and the wing is kind of in a horizontal flat position. So the bending loads there need to be considered for tilt rotor on a big scale, whereas for a tilt wing, you still have potentially the rotors far out. You can put them further in on the wing. And also because the wing is upright, it's like a nice rigid beam to take up exactly these point-wise loads to generate the lift. But yeah, on size, like on UAV size, so the smaller sizes we're working with, I think this is less of a problem. Another thing might be that tilt wing generally starts to generate lift a bit earlier, because the airflow is well aligned with the airfoil. So the prop wash, which hits the airfoil, is somewhat nicely aligned, generates a force flow over the wing, has maybe some better stall behavior, but I think it's hard to give a general answer here. For sure, a disadvantage of the tilt wing, as it's also covered in the case studies, that it's pretty susceptible to horizontal winds in hover. So really, with this large wing surface being upright and potentially facing into the wind, you're having a hard time flying at some decent speeds forward. Yeah, maybe Mike, you can add your experience on tilt rotors there a bit.
Yeah, I mean, I sort of agree that it's hard upfront to say which one would be preferable compared to the other. So, yeah, I mean, as you said, it really depends on the application. Maybe one more thing, so that tilt wing to me seems also in terms like aerodynamic modeling, it's a bit more complex, because you actually have to model the full region, including stall, which is generally a bit more difficult. But on the other hand, it also gives you the possibility to, for example, slow down. So I briefly touched on this, but for tilt rotor vehicles, if you can't tilt your rotors backwards, you can't really slow down very efficiently. Whereas if you, I guess for the tilt wing, if you go into stall sort of forcefully, you can slow down rather efficiently. So again, you have this trade-off between the platforms, which ultimately you need to decide on what you want to favor.
Regarding the wind in hover, especially for the Wingtra case, if it's basically better to, if this is now the Wingtra, instead of having the wind from this direction, having it from the side, if that would be better in hover. We did also think about that, and we tried it. And the problem with that is that it will actually be less affected by the wind in terms of it will not produce as much drag, but this is actually a very unstable situation. So if you have a slight deviation from the wind being exactly perpendicular, if you wouldn't do anything, the wind would always force it to be again aligned like this. So you would need to actively control it to always be like that. And because it's unstable, it's actually pretty difficult. So you always are kind of between these two states, would trigger kind of switch around it, just because it is not a stable situation. So in the end, it was, we tried it, but it was in the end almost more difficult, because also then you constantly need to have differential flap deflection, which then also kind of can create weird aerodynamic effects. And in the end, it was easy to just try to control it in this situation, with also having the advantage afterwards that having wind also created lift and reduced in total the power consumption. I hope that answered the question.
Then there's next question on the tilt wing and whether it would be beneficial to have like both wings, so left and right, tilt independently. So yes, I think you could omit like the ailerons, which right now are used to control yaw and hover, and then also roll and cruise. So it's actually an interesting thing that we've also been discussing currently in one of the running focus projects, whether it would be useful to have like separately tilting wings. So one advantage would be that you have really quite a lot of control authority, especially for yawing in hover. Probably too much control authority for rolling in cruise because you tilt the entire wing. Typically for say a fixed wing, it's enough to have like small ailerons for roll control. Then one of the disadvantages I would see there is that if you have like only a little bit of like mechanical slack, for example, or just play in this mechanism to tilt the wing, and then the left and the right hand side are able to tilt a bit independently. So if you cannot perfectly control them, you can potentially have quite high roll torques, which are generated in cruise. And so, yeah, the system would become really responsive and maybe too responsive for like what you can do mechanically to control the tilt angles, because really small differential tilt in that sense would probably yield already quite high roll rates. So if you have just one wing which is stiff and constructed, well, maybe it still has a twist because of construction errors, but you can trim this out with the ailerons, like the neutral position of the ailerons. But then the entire wing tilts as one piece, and even if there you then still have like mechanical slack on the tilt, it at least doesn't induce like roll moments during cruise flight. So it would make you quite agile, could be beneficial in hover, but probably somewhat a mechanical design problem in cruise. You would really need to make sure that the servos are doing their job properly then.
So I may add one thing to that from David's explanation. So if you remember in the just the fundamental slides for the fixed wing lecture where we looked at the range of angles of attack that we actually operate in. So this still applies even if you're talking about a tilt wing. So something like, you know, -2 degrees angle of attack to like 10 degrees angle of attack. So there's only like a 15-degree range that's actually safe, that you're not stalled for angle of attack. But you have a very wide difference in lift throughout that whole region. So as David was saying, if you have very small, you know, differences from what you expect on your servos for tilting the whole wing, so that's a really, really large increase in lift and drag just for a very, very small angle. And so that would have to be super, super precisely controlled. You also have the whole surface area to consider when you're generating this lift versus if there's just an aileron changing the camber a bit, this doesn't increase the lift that much. So then, of course, differential makes huge roll moments like David was mentioning. But just call back to the lecture, basically, that there's really only a very small range of angle of attack that causes very big differences in lift.
Yeah, maybe one last point is also in terms of mechanical integrity. Like if you basically have the wings separately, you can't really connect them. So this just, yeah, for structural integrity, it's not really beneficial, I guess. So maybe also on the diffuser design, if you remember, the wings are actually connected on the leading edge, which gives quite a lot of stability. So of course, if you want to do them differentially, you can't do that. Then I guess for the spoilers, to break down the tilt rotor, this would indeed be an option, yes. So we actually also thought about it during the project that I presented. So here one option would be, or one option which we discussed was to basically use the rudders to sort of face in, for example, both inwards or both outwards to slow down. But actually the platform that we have was mechanically impossible to do it this way. But yeah, I mean, you're right. It would be an option to improve the braking behavior, definitely.
Okay, then maybe on the next question, whereas like all the designs have the props on the leading edge of their wing, where there's a fundamental reason. So I think speaking for tilt wing, but also for tail sitter. So if you like were to choose freely where to put the props, I think so the main benefit of having them on the leading edge is, I think, that you have like the force flow state over the wing. So if you were to put them in the backside of the wing, so at the bottom, I think you could still fly this platform, but you would have the wing always just in, or probably would still feel that there's a propeller right behind it, but overall it's more or less in the free stream. And so then for all the high angles of attack that you have in like cover phase and like say early transition towards cruise, the wing would be just stalled, and in that sense mostly generating drag, but you couldn't benefit from that force flow state over the wing, which also helps to make, as I think, so from what I've seen or the experience of piloting this platform, it makes the stall behavior more benign in that sense. So you kind of blasting the throttle is always kind of a safe way out in case something gets a bit uncomfortable, because you can then kind of force the flow of the wing. You can kind of blow away, like that's kind of an image, kind of blow away the stall regime on the wing in case it would happen if you're like in a low throttle state and the wing stalls. Then yeah, you can pull yourself out quite easily that way. And if you have it in the back, the wing is really just always in free stream, and then it would probably be better to have it always oriented in a horizontal flat position as it's done for a tilt rotor. Maybe Sebastian?
Yeah, I agree there completely to what you say. So it's always kind of helps a lot if you would be in some stall-like region to just pump up the propellers such that you again can ensure some stream over the wing to kind of make also the control surfaces effective again. Another point that makes it a bit more difficult to have it in the, if it would be in the back, is when starting and landing, you have way more effects that you're very close to the ground. So it's kind of also, it makes just everything a bit more unstable there. So there wasn't really, or for our case where we thought about it, there wasn't really much of a, or we didn't see any advantage of having it in the back, only things that were rather disadvantages actually.
Maybe one quick other thing on this. So another callback to the fundamentals lecture. So I'm gonna plug this every time, just try to make the connections. So we talked quite a bit also in the review session last week about turbulent versus laminar flow. And so this whole slipstream from the prop wash that they've just been describing, so Dave and Sebastian, is turbulent flow for sure, because the prop is beating it to death and it's changing direction, pressure, velocity. It's got all these little eddies in there, but it's still attached in this case. So again, in the live lecture last week, we did quite some discussion on the differences between separated flow, turbulent flow, and laminar flow, and how both laminar and turbulent flow can still be attached or separated. And in this case, where there's a good amount of slipstream over the wing from the props, like on the Wingtra platform, for example, this is definitely attached flow. And that's why there's that control authority still there, because the control surfaces are still effective because that flow is still attached. So that's like a positive use case of turbulent flow. Of course, if you model this though, it will have a different, let's say, lift or drag characteristic than if it was purely in free stream. You'd have to separately identify those two things, which I think, you can correct me if I'm wrong, Sebastian, but I believe you presented that also in your case study, that you have a wetted area and a non-wetted area that have different lift and drag coefficients.
I think I had it in there, but that's one of the slides where I rather went quickly through it because it was pretty detailed, and I thought it's yeah, I anyway already took quite some time for everything. But I think it was in one of the slides.
Sure. Okay, but then simple explanation, basically that wetted area is assuming that we have this turbulent, prop wash coming over the wing. And so that's why the lift coefficient there would not be the same as, for example, one with just free stream flow over there.
So I guess for the large-scale aircraft, there have actually also been some large-scale tilt wing. I think actually David's platform is based on one of these. The thing is, in general, even for the Osprey, the development cost is rather high for these sort of vehicles. And also, I mean, if you look at the development process for the Ospreys, there have been multiple crashes, casualties, and so on. So I guess it's just inherently difficult to control and also construct these types of platforms, which is why we don't see them that often in reality, let's say. Yeah, I guess on the, like, why there are more tilt wings, more tilt rotors rather than tilt wings, I would, like, I'm not 100% sure, but I would guess it's due to the simplicity of modeling tilt rotors compared to tilt wings. But maybe David, you can. You also
yeah,
have some insight.
I mean, I'm not the expert in that, like for the manned aviation and developments there, but I just like recall that Osprey is kind of one of the great examples for the sunken cost fallacy, where it's just like development time was so much prolonged and everything. So I think also for tilt rotors, there are actually only two designs out there. I think the Osprey and then one kind of other civilian platform, which is still in development since I think 20 years. The initially Bell AW609, I guess, looks pretty much similar to an Osprey. And so they're just these two designs. And then like tilt wings, which haven't been seen since, I don't know, maybe end of the 70s or so. But there were a couple of designs around for tilt wings, but they were just not pursued any further. I think also the question is whether this is about the susceptibility to wind. This could be. I mean, this is definitely something where the tilt wing falls back short a bit. Yeah, otherwise, I think, again, for big platforms, a tilt wing might be a bit easier in construction because you don't need, so the Osprey, on the other hand, like has like two full like helicopter rotor heads for collective and cyclic pitch, so that you can, well, it's mechanically quite complex, whereas for a tilt wing, you just need collective pitch on the propeller so that you can quickly modulate the thrust, but you don't need to have like cyclic pitch as you have it on a big helicopter, because you also typically have another propeller in the back to do the pitch actuation. So I think wind is really pretty much the one downside of a tilt wing in that aspect. Yeah, but why there isn't these designs, I think in many cases it's also kind of a political development behind these projects that then decide whether they happen or not. Yeah. Hope this answers the question, but maybe we'll soon see again. So they're like within this, I mean, probably have seen a lot of designs recently about like urban air transport, air taxis, all these kind of things. There are a couple of designs for tilt wings out there. So maybe in the near future we see actually tilt wings again, but yeah, we'll see. Then on computation power to control such a system depends a bit on like which level you have a look at for control. So for the tilt wing, right, it's a pixel which is enough for attitude control, and maybe also some simple version of, say, velocity or cruise control. So currently we're working on an NPC for velocity or cruise control, which definitely doesn't run on a pixel. So there we rely on an additional computer on board. But like the low level stuff, I think there the pixel is enough for all these platforms.
Also for us, so we started with the PixHawk, and by now we have still a PixHawk equivalent microcontroller on it that does actually all of the control for us. So it depends a bit what kind of controller you want to run. Once it's MPC, I think Costas, right, teacher, I think once managed to put some MPC on PixHawk, but that was a rather tedious implementation. So I think generally once you want to go for model predictive control, it's pretty difficult to get it running on the PixHawk. But if it's something where it's just, let's say, a bunch of equations like regular attitude controller, that's no problem at all. Also, depending on how fancy you want to go with position control, there it's also enough. So if you use L1 or TEX, which might be in the lecture, yeah, those are also no problem to run on a PixHawk microcontroller. Once you want to also go more high level with like planning and collision avoidance, then I guess you will have, again, more problems running it on a microcontroller.
Yeah, so a quick note on the PixHawk MPC that Sebastian mentioned. So this was some work done by a postdoc in the lab. He's a professor now in Norway, but so he actually does really good work. So if you look up Costas Alexis, any of his papers, he has very nice papers. But anyway, while he was at ASL, he did implement a explicit MPC, and that's the main difference of why it was able to run on a microcontroller. Was because explicit MPC, so one, it's linear, so it's not nonlinear, it's not solving any kind of optimization in real time. What they do instead is they take the linear form, solve it for a bunch of conditions offline, and basically you make a gigantic lookup table for any kind of input condition you might have and what the optimal outputs are given the MPC tuning that you had offline. And also, it was only like 2 separate decoupled 2-state MPCs. So it was really, really lightweight. So it was like a pitch controller and a roll controller. And yeah, I think it was 2 inputs, 2 states for each, and in that explicit form. So then all you really needed to do for the microcontroller was just have a way to have all of this loaded up in RAM and ready to access, and then it'll work somehow. But like Sebastian said, it is actually pretty tedious to do this as well. And actually PID does a pretty good job on its own, if you schedule it properly.
I think I'm not the right person to answer the next question regarding lower drag when the propeller is in the back. I don't have a lot of experience there, so I honestly don't know the answer to that, if that is something that applies always or only at higher speeds.
Yeah, I'm also kind of not able to answer this. But just typically, like on these platforms, also in modeling, kind of still stay at the somewhat lower level where we, or no, higher level where we wouldn't consider kind of all these tiny little details that would, for example, be the cause for being like aerodynamically more optimal placement of the propeller in front rather than back. But typically when you design a platform, then, so I'm just using one off the shelf and trying to fly it. But if you were to design it, I think this might be really something also worth to consider. So I'm not exactly sure how to answer, but one aspect is like, I think aerodynamic design aspects for using jet turbines is a bit different than propellers because so there, I think, yeah, many like the inflow conditions there might be different, or for the turbine to like work more optimal. That might be something that influences things as well there. One thing, so mounting propellers in the back or versus mounting them in the front, one thing I could think about, like why it would be beneficial to have them in the front, especially for the wing, is that, so behind the propeller you have like not only axial induced velocity, but the flow also exhibits a swirl. So just the drag torque on the propeller means with action equals reaction that the fluid needs to exhibit like some angular momentum then as well. So you have this swirl behind the propeller, which is basically kinetic energy, which doesn't provide you any thrust. And then if behind the propeller, you kind of have at least one plate, which in some parts redirects the flow into an axial direction. This might kind of make it a bit more efficient, or generally having a rotor and then kind of a stator in the back to kind of take out the swirl of the flow and redirect it in axial direction. So this might help you or be a benefit of mounting in the front of a wing. Another thing, if you have it on the back side of a wing, it's typically more noisy, so this can be a bit annoying, but not really from an efficiency perspective. So I'm not sure on a definite answer here, but I think there's a lot to consider in general for these kind of things.
Yeah, maybe one more note just on the difference between jets and props. So there's quite some difference in how they even operate, which may be influencing whatever you read about the drag characteristics. So for example, props are trying to pull you through the air basically, and by generating lift, but a jet's actually sucking in the air and then just exploding it out the back. It's quite different, I guess, process. I'm also not so well versed in jets, I have to say. That's kind of my high level knowledge. Yeah.
Okay. Next question specifically to me on the platform is off the shelf. That's right. And so normally if you buy it like as it comes to actually fly it around, it comes already with attitude stabilization. So you don't have to do it manually. I would actually argue that it's almost impossible to do it manually, at least in hover. So generally, I think multi-rotor is really hard to fly manually in hover. I don't know, FPV pilots might say something different, but at least I cannot do it. So what it does is like, I didn't reverse engineer it, would be a bit hard, but it's just, I would guess, standard multi-copter hover controller, and then some fixed wing stabilization in cruise flight, and in between it has like a small potentiometer on the wing to figure out when the wing passes the like 45-degree angle, and then it really switches from one to another controller. I don't think they had like more scheduling based on the wing tilt angle as to how they mix, for example, differential deflection of the aileron and differential thrust on the props. Yeah, you can also not fly it in transition over longer times. So it's really just one switch and then the wing tilts up through the full range or down. So they try to minimize the time you spend in transition.
Okay, regarding the Wingtra in strong winds, so there's different mechanisms that we have. On one hand, we have a warranty for customers in which we say this is the wind that you can measure on ground and still take off with kind of still without voiding the warranty of it. But of course, the wind on the ground is not always the same as in the air, especially. Yeah, it depends a bit on how the environment looks like. But what we also do is we have some threshold. So once the wind that we estimate is above a certain threshold, where we still have enough of a margin to know that we can fly even if it picks up further, then we just abort the mission and kind of go back to the takeoff point and land again. Yeah, so I think that covers pretty much all cases. I mean, there's for sure wind scenarios where we wouldn't be able to fly anymore. I guess the latest point would be when with full thrust, you cannot keep maintain a 0 ground speed that we didn't have so far yet. Maybe one interesting case that actually one of our customer once had is that it was captured by like a small tornado. So there we actually weren't able to land, but there was actually only minor damage, which was surprising. But yeah, that was something that we never tested. which you can also not easily test. Okay, next question is also for me. Why using the difference of actual and commanded angular velocity instead of using only the measured one? That's a good question. Generally, it depends a bit on the structure of the controller that you have. I think the way I had it in the slide is where I had both kind of a gain times the attitude error plus a gain times the angular rate error. So what we use as commanded angular velocity there is kind of, I didn't state there. And especially in the beginning, we just had it 0. So it would be the same as you suggested in your question. But it could be that for certain recovery mechanisms or maneuvers, you still want to have like an additional feed-forward like term from the attitude controller point of view there. So to just kind of in most of the cases, it probably would make sense the way I wrote it down to have it 0, but there could be certain maneuvers or recovery strategies where it could make sense to also add some additional attitude rate reference there. One also what could make sense, I mean, I guess not for our case, but generally if you also want to have a rate controlled mode, then it kind of makes sense to also allow that. And once you go higher to the attitude controlled mode level, as it might make sense maybe for FPV drones where you might want to be able to fly with both, where there you then either use the attitude error as the input or the attitude error as the reference of the angular rate reference, or have them separately instead of cascading them, just having both as contributing to the moment. And you can actually show mathematically that you can bring the two versions of one time cascaded and one times both directly to the moment, that you can bring them into an equivalent form. I hope that more or less answered the question.
Okay, so looks like it's the end of the questions, but anybody maybe in the next 30 seconds or so has another question for Sebastian, David, or Mike, please put it in the chat. Otherwise, you will lose your chance for a face-to-face interaction with them forever. So maybe I can actually answer the bottom question real quick. So about semester projects on these topics. So at the moment on the website, there may not be any posted specifically about tilt rotors or tilt wings, but likely sometime in January, we would post a couple more. So right now there's some other projects wrapping up and we don't know exactly which direction we're headed yet. So David would probably post something. I'm not sure what Mike is wanting to post in the next month or so, but possibly he might have something as well. So just be on the lookout, I guess, in January, and we'll have a better idea what's coming up in the lab, what projects are globally happening, and what kind of semester projects can contribute to this.
I guess for the question before, I cannot give you a specific one, but I think there's many that are based on PixHawk, especially if you also want to kind of have control yourself of the software and getting an understanding and tuning it and play around with maybe different controllers. So there's for sure things with PX4 which is the software that runs on the PixHawk Autopilot. Or also, I have mainly experience with that. There's also Ardu Pilot ones that I think run even on the same hardware, but are different software. So I guess you can there look in the internet of some DIY kits where you can build together a quadrocopter, or actually even small tail sitters and tilt wings. I think that might also be supported there. There's also other open source autopilots like Paparazzi's, I think, one. Probably more, I don't know all of them. I personally only have experience with PX4.
Yeah, maybe another note on that. So if you go to PX4's webpage, I believe it's just px4.io. Maybe I'll put it in the chat here. See everyone, px4.io. So it's in the chat. So they actually have quite nice documentation for everything nowadays. They didn't used to, but now they really have tried to make it to where it's a user-friendly autopilot, and you can kind of see what's going on under the hood at whatever level you're comfortable with. And so the other thing they have on the webpage are supported airframes. So there's a bunch of kind of off-the-shelf hobby aircraft that people just put PixHawks into, and a few of those at least are quote supported airframes that would already have a standard controller in the PX4 software, that if you bought that given hobby plane, you'd have a starting point already. You'd just have a working controller, mostly. Maybe you have to tune it a bit. The estimator will work. You don't have to set up any of the low-level stuff like this. You just plug in the ESCs, choose the right airframe in the software, and then hopefully it should at least somewhat stably hover and maybe take off into fixed wing mode if it's a transitionable kind of plane.
And in case you want to go even more the DIY way, there's also in a lab where I have been working in the US, they actually built just from 2 wooden planks like a cross, and then used motors that they had lying around with ESCs and connected that to a PixHawk, and they also made that fly. So in case you have motors and motor controllers lying around, you could also even do something in that direction. It might require though a bit more tuning because it's not off the shelf.
Okay, so it's noon now. Any last minute questions for our speakers? Otherwise, so you can also post questions into the Piazza if you think of something later. And then hopefully one of the guys can get around to checking it. And then tomorrow we'll have the exercise for fixed wing. So basically, just to give you a quick overview of what it'll be, it's we're just going through kind of the standard process of how do you tune a cascaded PID controller for a fixed wing aircraft. And this is actually the process we take for any kind of new fixed wing platform we want to fly. We really go step by step, set the manual controls, see if we can stabilize it at a level, steady airspeed, and then start with some rate damping, basically just to reject any kind of disturbances, move on to attitude stabilization so we can say, okay, yeah, be at this pitch or at this roll. And then we step it up to the high level even with so text and L1. And yeah, so all the files are online, the MATLAB scripts and the Simulink model, so you can already play with it tonight if you want, and then tomorrow we'll go through. So I guess everyone can give a nice emoji round of applause for the 3 speakers of the case studies. I think they had some really nice content to share with you and experience. Yeah.
Thank you very much.
Thanks. Yeah, thanks for the interest and the questions.
Okay, but then I guess we'll end it there. So do I have the option, Mike, to hit the stop button on recording?
I do have it. I can stop.
Oh, you can do it. Okay. Okay, then we'll also upload this this live recording so you can come back and